Today we'll be discussing angular momentum and later conservation of angular momentum. Remember earlier we wrote Newton's second law in terms of linear momentum, such that the net force was equal to the time derivative of the linear momentum. We also know that torque is the position vector crossed with the force, so if we take the cross product with position vector of both sides of this equation, we get a net torque on the left-hand side and a derivative of a new quantity on the right-hand side. This new quantity we will call L, or the angular momentum. So we can write the net torque is equal to the time derivative of the angular momentum, where the angular momentum is given by the radius vector crossed with the position vector. However, there's an easier way to write the angular momentum, which we can see by using a couple of facts that we already know. First, that the linear momentum is the mass times the linear velocity, and secondly, that the magnitude of the velocity is given by the magnitude of the position vector times the magnitude of the angular velocity vector. Finally, this cross product, r cross p, means that the angular momentum is perpendicular to both the position vector to some point, as well as perpendicular to the linear velocity of some point. But this is exactly the direction that the angular velocity vector points. So putting this all together, we get that the angular momentum, which is the position across the linear momentum, is equal to mr squared times the angular velocity vector, where one factor of r squared comes from the original r cross p expression, and the second factor comes from substituting omega for v. However, we know that mr squared is simply the moment of inertia of a point particle, so we get that the angular momentum L is the moment of inertia times the angular velocity vector. All right, well, we had this expression from before that the sum of the net torques equals the time derivative of the angular momentum. But this implies that if the net torque acting on a system is 0, dl equals 0, so angular momentum of the system does not change. Note that this does not mean that no torque acts on the system. It just means that the net external torque must be 0. So the angular momentum of a system can be constant even if there are several forces acting on it, so long as the net torque exerted by those forces is equal to 0. It's useful to compare this to conservation of linear momentum. In the linear momentum case, conservation of momentum usually meant conservation of center of mass velocity. Since linear momentum is mass times velocity, conservation of linear momentum means the product of mass times velocity can't change, and almost always the mass of a system does not change, with the notable exception of being a rocket. So, as long as we're not dealing with rockets, if the mass of a system is constant, that means the center of mass velocity of the system is also constant. However, in this case, the moment of inertia is dependent both on the mass of the system and on how that mass is distributed. So the moment of inertia of a system can change even if the mass of the system stays the same. So as long as angular momentum is conserved, it's actually fairly easy to change the angular velocity by changing the moment of inertia, in contrast to linear momentum, where it was fairly hard to change the center of mass velocity, because almost always mass is a constant. Let's look at a couple of examples of how we could use conservation of angular momentum to see how angular velocity could change. First of all, suppose you are sitting on an office chair or stool or something that can easily spin. Suppose you start spinning while holding both your arms and your legs out from your body. If you then pull your arms and legs in, you decrease the moment of inertia of the system. The mass of the system of you in the chair doesn't change, but it's located closer to the axis of rotation now. Since moment of inertia is the sum of mass times radius squared, decreasing the radius, pulling your arms closer into your body, decreases the moment of inertia. We also know that the net torque on the system is 0. Nothing is trying to get you and the chair to spin faster or slower, so angular momentum is conserved. So putting these two facts together, decreasing the moment of inertia while conserving angular momentum means that you must increase the angular velocity, so you start spinning faster. Conversely, if you then let your arms and feet move outward, then you're increasing your moment of inertia again, so your angular velocity must decrease, and you start spinning more slowly. Let's look at another example. We can also change angular velocity by exchanging angular momentum between parts of a system. So suppose a person is sitting on a stool that is free to rotate, but the person is not initially rotating. They're holding a spinning bicycle wheel that is oriented horizontally in front of them. If the person slows the wheel down by holding the wheel against their chest, the angular momentum of the wheel alone decreases. However, the net torque on the person-wheel system is zero, so the total angular momentum must not change. The person therefore starts spinning in the same direction that the wheel initially was. In other words, initially the person alone had no angular momentum, and the wheel had some non-zero angular momentum. Afterward, if the wheel is brought to a stop, the wheel alone has no angular momentum, but the entire system can't have changed its angular momentum. So the angular momentum that was initially in the spinning wheel must have been transferred entirely into the person. So the angular momentum of the entire system hasn't changed, but the object inside the system that is holding the angular momentum has changed from initially the wheel to finally the person. All right, that's it.